When you ask a chatbot to rewrite a quick email, the process feels weightless. You type a prompt, press enter, and the answer appears instantly. But that single query travels to a physical data center, triggering an intense wave of computations across hundreds of servers at once. And as those processors crunch your data, they immediately generate a massive amount of physical heat. For the simplest tasks, one prompt processed by a popular model like GPT-5 uses about as much electricity as a 3-watt LED light bulb left on for 20 minutes, and requires a little less than a teaspoon of water to keep the servers cool. For a single user, that is a trivial amount, but OpenAI estimates it receives 2.5 billion queries every single day. Add that up, and you are looking at enough water to meet the daily drinking needs of every person in Monterrey, Mexico, and the energy footprint is just as steep. That same daily volume requires enough electricity to stream high-definition video continuously for 3,000 years. The number of AI users is expected to roughly double over the next half-decade. This software leap is drawing directly on physical, planetary resources, and the infrastructure needed to support it is multiplying. Stopping computers from melting is a legacy engineering problem. Even the first massive calculating machines in the 1940s relied on dedicated fans and ventilation to cool their vacuum tubes. Today, our microchips are trillions of times more powerful, generating immense thermal output. In a modern hyperscale data center, nearly 50% of the facility's total energy use goes strictly toward running the air conditioners and fans needed to stop those chips from frying. To reduce that massive electricity bill, many operators rely on evaporative cooling. By building data centers near massive sources of naturally cold fresh water, like the Great Lakes, they can spray water into rooftop towers to cool the servers through natural evaporation. It cuts the cooling energy needed by up to 60%, but the trade-off is a staggering drain on local resources. In 2021, one hyperscale data center in Oregon consumed nearly a third of its host city's entire public water supply. The alternative is moving facilities to arid climates, like Arizona, and using traditional air cooling. That saves the local water supply, but requires giant fans pushing air around the clock. The electrical strain is immense. In Ireland, data centers now consume a fifth of the country's entire public electricity grid. Engineers are caught in an impossible loop: either drain a community's water budget or max out its power grid. To break out of this cycle, the industry is pursuing extreme alternatives. The first logical escalation is to stop wasting energy air conditioning a massive warehouse and instead target the heat exactly where it is generated. Looking at this simplified cross-section of a microchip, we can see how direct-to-chip cooling works. A water-based liquid coolant circulates across metal plates, usually copper or aluminum, that are attached directly to the processing chips. Because liquid is much denser than air, it absorbs and moves heat far more effectively. This closed-loop system cuts the power used by server fans by up to 80% and requires zero on-site water consumption to operate. Curious, slightly amazed tone. But operators are pushing this idea even further by dunking an entire server rack into a chemical bath.
This is immersion cooling. The servers are submerged in special non-conductive oily liquids that won't short-circuit the electronics or rust the metal. It removes the need for fans completely. One immersion operator reported that 97% of their total energy now goes directly to computing instead of cooling. While liquid cooling is highly efficient, facilities are still running out of physical land and cheap electricity. The hardware is running so hot that tech companies are looking beyond traditional buildings entirely. They are turning to the open ocean, using the frigid waters of the Earth's seas as an infinite natural heat sink. In regions like the North Sea, companies are dropping massive 46-ton sealed capsules packed with high-density server racks straight to the ocean floor. Submerged in a non-conductive coolant, the heat naturally emanates outward into the freezing seawater. There are no fans, no lights, and no circulating pumps. This theoretically pushes computational efficiency to 99%, while cutting power consumption and carbon emissions by 40%. But the ocean is hostile. Hardware fails constantly, from network glitches to memory errors. If a server is on the ground, a technician replaces the faulty GPU in minutes. If it is sealed inside a pod at the bottom of the sea, routine maintenance becomes an expensive logistical nightmare. The ocean offers perfect thermodynamics, but terrible accessibility. To find an environment that might offer both, some engineers are looking straight up. Tech billionaires are exploring the ultimate infrastructure extreme, launching AI data centers into orbit. In 2026, Elon Musk merged SpaceX with his artificial intelligence company xAI to study the feasibility of space-based servers. The theory is that orbiting computers could rely on constant solar power while utilizing the deep freeze of space to naturally cool the hardware. As this diagram shows, there is a severe flaw in that logic. Space is a vacuum. Without an atmosphere to conduct heat away from the electronics, the thermal energy simply becomes trapped inside the casing. Objects in direct sunlight in orbit can bake at 120 degrees Celsius. Furthermore, low Earth orbit is already crowded with over 11,000 satellites monitoring climate change and global agriculture, making physical deployment incredibly complex. The engineering ladder has reached a physical limit. We cannot outbuild, outsync, or outlaunch the sheer amount of thermal energy generated by brute force AI computations. Pushing data centers into increasingly extreme environments only addresses the symptom. The most realistic solution is preventing that heat from being generated in the first place. Software engineers are advocating for a small data approach. Instead of brute force programming AI with millions of possible scenarios, which requires massive continuous server loads, models are taught in small, deliberate steps. As users, we also dictate the physical footprint of this technology. We can choose to run queries through less water-intensive language models or simply shift workloads to cooler hours of the day. The convenience of an instant AI response hides a massive supply chain of hardware, electricity, and water. The cloud is not weightless. Behind every automated email is a tangible cost paid by local communities, and we have to decide if that calculation is actually worth it.